Hi everyone, welcome back. The learning goal for this video is to be able to draw the orbital diagram and write the electron configuration for an element. And so in the previous video, we learned about sublevels. We learned about S, P, D, and F sublevels. We learned about how the period number tells us the principal quantum number n, that n equals 1 is lower in energy, and as we increase, we get higher in energy. And that the principal quantum number also tells us the number of sublevels. So n equals 1 has 1 sublevel, n equals 2 has 2 sublevels, 2s, 2p. n equals 3 has 3 sublevels, 3s, 3p, 3d. And n equals 4 has 4 sublevels, 4s, 4p, 4d, and 4f. And that's as high as we will go in this class. But what you will learn by the end of this video is that when we start determining orbital box diagrams and electron configurations, we will follow the order of occupied sublevels on the periodic table. So it'll be 1s, and then 2s, 2p, 3s, 3p, 4s, 3d, 4p, so on and so forth. We will follow that order. We will start with orbital diagrams. I always found that if you can derive the orbital box diagram, then you can translate it into the electron configuration. So orbital box diagrams use boxes to show how electrons are arranged in the orbitals of an atom, because that's our whole goal here, is figuring out where are these electrons located, what types of orbitals are they in. And I like to think of orbitals like available apartments for the electrons to spend their time in. So you will fill the orbitals and energy levels always from lowest to highest energy level. And then you will fill the orbitals within the same sublevel one at a time. So half fill them first before you start to partner them up. And you'll see me show this over and over again with different examples. So for example, the 1s orbital we represent with a box, and each box can hold up to 2 electrons. Because there's no other orbitals in the 1s orbital, it's just this one box, then I put an arrow pointing up and an arrow pointing down. In the previous video, we learned that electrons in the same orbital have opposite spin, which we represent by these arrows going up and down. And then you fill up 2s, because it's the next energy level to fill up. And then it can only hold up to 2 electrons. But 2p, notice how we don't partner them up, because the p sublevel we learned in the previous video has 3p orbitals, and they're all the same energy. So that's why they're all the same color here. And we half fill them first before we were to partner them. The way I remember that is, let's say I have a house with 3 rooms, right? And all on the same floor. So if I have 3 people wanting to rent this house, they will all want to get their own room as much as possible. Now, if I have a 4th roommate, then that person's going to have to share a room with one of the other roommates, right? And so you think of that, if they're all the same energy level, think of kind of all the same house there, then they will spread out as much as possible as they can. But if they have to partner up, let's say there's a 4th individual, then they will. Now, chemists use a notation called electron configuration to indicate the placement of electrons in an atom. So this is like the electron-specific address for their apartment, okay? So this will help us show how electrons fill the energy levels and the sublevels in order of increasing energy. So you will always start every electron configuration with 1s. And then you can also write an abbreviated form using a noble gas to represent the electrons preceding it. I will show both ways, the long version and the abbreviated version, for writing electron configuration. And this is an example of carbon. Now, before you do electron configuration or orbital box diagram, you got to figure out the number of electrons the element has. And that will use knowledge from a previous video. And once again, remember, we learned how to find the number of protons from the atomic number. And in order to determine the number of electrons, we assume the element is neutral here, just carbon that had no charge. So if it's neutral, then the number of protons is equal to the number of electrons. So for carbon, we have 6 electrons total. And when we write electron configuration, we write the type of orbital, and then the superscript represents the number of electrons. So this one is 1s2, 2s2, 2p2, and notice how the number of electrons, 2 plus 2 plus 2 is equal to 6 electrons. And this will be a core chemistry skill, learning how to write electron configurations. So let's look at some more examples together. So starting with hydrogen, which has only 1 electron, atomic number 1, 1 proton, 1 electron. The lowest energy orbital is always the 1s orbital. And so that electron is going to be represented by an arrow for the orbital diagram. But to translate that to electron configuration, we write the name of the orbital 1s, and then how many arrows are in that box. So 1s1. Helium, if we go back to our periodic table, has atomic number 2. So that's 2 protons. And because this is a neutral atom of helium, then we have 2 electrons. And so therefore, once again, start with the lowest orbital, and that, lowest energy orbital, which is 1s. So we draw our 1s box. And because there's 2 electrons, they will fill up, one pointing up and one pointing down to represent the opposite magnetic spin that we learned about in the previous video. And to translate the orbital box diagram into electron configuration, we write the type of orbital and then the number of arrows, which represent each electron. So this is a 1s, and then because there's 2 arrows, this is 2 electrons, so 1s2. Now, period 1, remember that periods represent the horizontal rows on a periodic table, but also represent the principal quantum number n. N equals 1, n equals 2, 3, 4, so on and so forth. So period 1 elements are hydrogen and helium, and this is both their orbital diagrams and their electron configurations. Let's look at period 2 elements. These are elements from lithium to neon on the periodic table. So once again, you'll always kind of fill this up first, 1s, before moving on to the next lowest energy orbital after 1s is 2s. And then after filling 2s, we'll start filling up 2p. But remember, in a p sublevel, there's always 3p orbitals. So notice how there's always 3 boxes all connected together in a row. All right, so starting with lithium, because it's atomic number 3, it has 3 protons, 3 electrons because it's neutral. So you would draw the box for the 1s orbital, the box for the 2s orbital. Each box can hold up to 2 electrons, so it'd be 1, 2, 3. So when we translate the orbital box diagram into electron configuration, we would write 1s, 2, 2s, 1, and that's the electron configuration for lithium. Now the abbreviated electron configuration takes the noble gas above it. And what I mean by that is that if we look at lithium, the noble gas that precedes it is helium. And that's because lithium has 3 electrons and helium has 2 electrons. We can't use neon. Neon is too far away and has more electrons than lithium does. So when you do the abbreviated electron configuration, you find the noble gas that precedes, or in other words, has fewer electrons than the element you're trying to write the electron configuration for. So for example, helium, we already determined on the previous slide has an electron configuration of 1s2. And so for lithium, we determined it was 1s2, 2s1. Basically, that helium is 1s2. And so to write the abbreviation, we could just do brackets helium, and then what's left over, 2s1. And that will help translate. If we use the abbreviated method, that will help our audience to understand that it also has electrons that look just like the electron configuration of helium for this noble gas. And it's going to save you a lot of time and space to learn how to do the abbreviated electron configuration for elements in n=3 and greater. It may seem less pertinent for this one here, but as you get more electrons, the abbreviated version does help save space and time in writing it. Beryllium has atomic number 4, so 4 protons, 4 electrons. Still always start with 1s, fill that up first, then 2s. So we have 1s2, 2s2 in these boxes. That's translated here, but you can also write the abbreviated with the helium because it precedes the beryllium. And when we get to boron, so we learned this is actually the S block. So that's the S. We finished beryllium, which was, ended up being 1s2, 2s2. But when we get to boron, now we're in what's called the P block. So we're going to start filling up the P sublevel here. This is the P block. And boron has 5 electrons, so 1s2, 2s2, but then it has, that's only 4 electrons, we need 5. So then we start filling up the 2p sublevel. And so that is 2p1. And you can see the full electron configuration written as such. 1s2, 2s2, 2p1. But once again, helium is the preceding noble gas. We could always write the abbreviated electron configuration. What's not highlighted is what's left over and needs to be included in the abbreviated electron configuration after that noble gas. We've seen carbon already, 6 electrons, but notice how they are unpaired. So unpair them first. Remember, think of the apartment analogy where, your apartment may have 3 bedrooms. And so if there's 3 roommates, or 2 roommates in this case here, they're going to take 2 separate rooms before partnering up. And nitrogen has 7 electrons. So we see all 3 are unpaired here, 2p3. Oxygen now has 4 electrons in the 2p level, 2p sublevel. And notice how we have filled them first, and then we had to put that 4th roommate. That 4th roommate had to share a room with one of the roommates. Fluorine has 9 electrons, 1s2, 2s2, 2p5. I half fill them first and then partner up the next 2. And then neon has 10 electrons total, 1s2, 2s2, 2p6, and everything is filled, no unpaired electrons. You can also always check your work, add up your superscripts. 2 + 2 + 6 is 10, which is the number of electrons for that element in neon. So the guide to drawing orbital box diagrams is first draw the boxes to represent the orbitals as you saw in the previous examples. Step 2 is place a pair of electrons with opposite spins in each filled orbital. So like 1s2, notice how with 1s2 you drew a box and you have 1 electron pointing up and 1 electron pointing down. So they have opposite spins. Step 3 is to place the remaining electrons in the last occupied sublevel in separate orbitals. So for example, when we had the P sublevel, we had to half fill first before we were to partner up if there was a 4th electron there. So let's practice. So nitrogen atoms are found in amino acids, proteins, and nucleic acids, a very common element in the body. Let's practice drawing the orbital diagram for nitrogen together. So once again, the orbital box diagram, we draw the boxes first, and notice how the order is always the same. So start with 1s, and then 2s, and then 2p. And then what you do is you go to your periodic table, you find the element you're looking for, so nitrogen, you determine the atomic number, which tells you there's 7 protons, and because there's 7 protons for a neutral nitrogen atom, there are 7 electrons. And then you start to fill up your boxes with arrows. Each arrow represents an electron. So I have 1s2, 2s2, and so I have 4 electrons, I have 3 left, and I need to half fill these because the 2p sublevel, they're all the same energy. So they're gonna spread out and they're not gonna partner up. They're not gonna share a room if they don't have to, okay? So this is the orbital box diagram for nitrogen, and the number of electrons should equal to the number of arrows drawn. So as you saw here, we already placed a pair of electrons with opposite spins in the filled orbital, and then we placed the remaining in the last occupied sublevel, which is the 2p sublevel, and we half fill them first in separate orbitals in separate rooms. Period 3 elements, those are located in n equals 3, that's sodium to argon. And this is showing you, first of all, if we're looking at sodium, the preceding noble gas, go backwards, is neon. Okay, so sodium has 11 electrons, neon has 10, so that's the preceding noble gas. And so the way you read this example here is they're showing you neon. Neon is 1s2, 2s2, 2p6, so that's that. And then they're showing you the boxes for the 3s and 3p orbitals only. Because once you fill up 2s2, 2p6, that's neon, 2p6, then you start with 3s2 or 3s1, 3s2, and this is 3p6. So then the p blocks of 3p. And so that's kind of how you're going to fill it up. You fill up the 3s before the 3p. The 3p is higher in energy than 3s. And so sodium has 11 electrons. 10 of them kind of make up neon's electron configuration. And therefore the last electron, number 11, has to go in the 3s orbital. Magnesium has 12 electrons. We have 3s2. Aluminum has 13 electrons, but then we fill up the 3s2, and then we start to fill up the 3p. That's the next energy level. 3p1. Silicon, it's got 14. So it's got neon's electron configuration, if you did the abbreviation, followed by 3s2, 3p2. Notice how silicon and phosphorus, like these elements, we're half filling them first before we partner them up, just like we saw with the period 2 elements. And then last but not least, argon has 18 total electrons. 1s2, 2s2, 2p6, 3s2, 3p6. But once again, using the abbreviated version is also very helpful. It saves you a bit of time. So the electron configurations of elements are related to the positions on the periodic table, and there's different sections or blocks corresponding to the sublevels S, P, D, F. I've already showed that to you, but I want to reiterate that. This is the S block, the D block, the P block, and the F block. So 1s2, 2s2, 2p6, or no, sorry, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2s, and we won't go like any more than that. But basically, this kind of gives you the order looking at the periodic table of the electrons. So you fill up the 1s before you do the 2s. After the 2s is the 2p. After 2p is 3s. After 3s is 3p, so on and so forth. So you could really use the periodic table to help you determine electron configuration quickly. So if I gave you an example here on the periodic table, let's say I wanted to do sulfur, and I want to read off the periodic table, then I would start, I know this is 1s, so 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 3p4. So you can just use the periodic table as long as you know the blocks S, P, D, and F, although we won't be working with F. We'll be focusing primarily on S, P, and D in my course. So this just summarizes what I've shown you. The S block contains elements in groups 1 and 2. This means the final 1 or 2 electrons are in the S sublevel. The P block consists of elements group 13 through 18. There are 6 P block elements in each period because 3 P orbitals can hold up to 6 electrons. Remember, each orbital holds up to 2 electrons, but since there's 3 P orbitals, that P sublevel can hold up to 6 electrons. D block contains the transition elements. Those are in the middle. It first appears after calcium, and there are 10 elements in the D block because 5 d orbitals can hold up a maximum of 10 electrons. And the F block are called the inner transition elements, and it's the 2 rows of elements at the bottom of the periodic table, the lanthanides and actinides. And there are 14 elements in each F block because 7 orbitals can hold a maximum of 14 electrons. And this is going to be a core chemistry skill, being able to use the periodic table to write electron configurations. Because once we can write the electron configuration of any element, we can understand its properties. And we are going to use that knowledge to predict what kind of compounds or molecules that element will like to form, whether it'll form ionic or covalent compounds in a later video. But it's important we master electron configuration first before we start building molecules and compounds. So a guide for writing configurations using the sublevel blocks. First, locate the element. Write the filled sublevels in order, going across each period. So you heard me go through and say, okay, 1s2, 2s2, 2p6, 3s2. So you do the filled sublevels. And then you complete the configuration by counting the electrons in the last sublevel block. So if we were looking at chlorine, it filled up 1s2, 2s2, 2p6, 3s2, but it stopped at 3p5. It's not full. So let's walk through that one together. So 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5, 3p5. Oh, there we go. All right. So period 4 elements. The order is a little bit different here. So we have the 4s sublevel fills before the 3d. Because the 3d sublevel is slightly lower in energy than the 4s sublevel. And the 5s sublevel fills before the 4d sublevel, and the 6s sublevel fills before the 5d. This actually is an oversimplification. There's a lot of exceptions to the rules because these d and s orbitals are actually quite close in energy, but we won't be diving into that too much in this course. So what I mean is that here, this is 4s. And where you start with scandium, this starts with the 3D. So we have 4s, 3D, 4P, and then 5S, and then we have 4D, 5P. And so that will take a bit of practice, but we will work through that together and remembering the order in which we fill them using our periodic table. And so you can see scandium is 21 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Let's look at that. So 1s2, 2s2, 2p6, so 1, 2, 3, 4, 5, 6, 3s2, 3p6, 4s2, 3d1. So this is the 3d row there. Now there are exceptions to the rule, because you'll notice that titanium, we fill up 4s2 and then 3d2. Vanadium is 4s2, 3d3. But chromium and copper are exceptions to the rule. And like I said, there's definitely exceptions with these transition elements. And copper and chromium are the ones we cover in this class, where the 4s is not full. It is not 4s2, but rather it's 4s1, 3d5. And copper is 4s1, 3d10. So atoms are always going to find the lowest energy configuration as much as possible. And that's just the case here. It is lower in energy of being 4s1, 3d5 than it would have been 4s2, 3d4. And same for copper. But I wouldn't stress too much about exceptions to the rule, because like I said, there's a lot more to it than I'm able to cover in this course. And then you can see here, these are examples of more electron configurations that have the P block. So once you finish the 3D10, then you start the 4P. So this is 4S, 3D, and this is 4P. So these are the 4P elements. And so gallium has, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. So let's walk through that using the periodic table slowly. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. And I encourage you, all the electron configurations and their abbreviations are given. I encourage you to try to do this on your own and then check your work with the notes. So if you did, for example, arsenic, did you come up with this electron configuration? And did you come up with this abbreviated electron configuration? All right, let's practice. I know there's a lot of information, but let's try it out. Pause the video, determine the electron configuration for selenium, and then come back and check your work with me. All right, first things first, let's find selenium on the periodic table. Atomic number 34, which means it has 34 electrons. I'm going to do the long version of electron configuration, and then we can do the short abbreviated version afterwards. So I'm going to walk through it. So I know it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 1, 2, 3, 4. So 4p4. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. So that's the long version. And make sure once again that the superscript is the number of electrons. So that's always a superscript, not a subscript. And this should add up to 34 electrons. The abbreviated version is that you would look at selenium and find the preceding noble gas, which is argon. So the preceding noble gas is argon, and you put brackets around it. And argon's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So argon is here. And so argon is this, and then I write the rest as is. So 4s2, 3d10, 4p4. And I do expect you to feel comfortable doing both long electron configurations and abbreviated electron configurations. So as a reminder, there are the two exceptions we're covering in this class, chromium and copper. So for chromium, moving one of the 4s electrons to the 3d sublevel adds stability with the half-filled d subshell, and the resulting configuration is 4s1 3d5. And for copper, moving one of the 4s electrons to the 3d sublevel adds stability with the filled d subshell, and the resulting configuration is 4s1 3d10. And so like I said, this is, we're not going into the reason why that is, but we're just understanding that it's adopting the configuration that makes it more stable and therefore more happy. And so that's all I care that you understand for those two exceptions. So having these all half fill is better than having one of these filling up the 4s2. And same thing here. All right, go ahead and pause the video, try the study check on your own, and then check your work with me. All right, let's use the periodic table to give the symbol and the name for the element with the electron configuration. So remember, electron configuration is like the element's address. And so you not only will be able to determine electron configuration of an element, but you can also use the electron configuration to identify the element. So if we're looking for 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. So we're going to take the electron configuration and walk along the periodic table together. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. So 1, 2, 3, 4, 5, 6, 7. So I got the answer to be cobalt. This is cobalt's configuration. All right, go ahead, pause the video, write the electron configuration for the following elements, and then check your work with me. Okie dokie, so let's start with my favorite element, carbon. 1s2, 2s2, 2p2, good. So let's write 1s2, 2s2, 2p2. And if we wanted to do the abbreviated for carbon, it would be helium, which is 1s2. So the abbreviated would be helium, and then whatever's left over, 2s2, 2p2. Silicon is here. So this would be 1s2, 2s2, 2p6, 3s2, 3p2. Good. So we have 1s2, 2s2, 2p6, 3s2, 3p2. And what is the nearest noble gas that precedes it? It is neon. Good. So then neon is 1s2, 2s2, 2p6. So this is neon's configuration. So what's left over? Sorry, that should have been a 2. 3s2, 3p2. Oxygen, 1s2, 2s2, 2p, 1, 2, 3, 4, 2p4. So 1s2, 2s2, 2p4. And its nearest noble gas is helium. So it'd be 2s2, 2p4. All right, thank you for watching. And as always, email me with any questions.